In organic chemistry, an electrocyclic reaction is a type of pericyclic rearrangement where the net result is one pi bond being converted into one sigma bond or vice versa. These reactions are usually categorized by the following criteria. Reactions can be either photochemical or thermal. Reactions can be either ring opening or ring closing, that is electrocyclization. Depending on the type of reaction, that is photochemical or thermal, and number of pi electrons, the reaction can happen through either a conrotatory or a disrotatory mechanism. The type of rotation determines whether the cis or trans isomer of the product will be formed. After studying this module, dear students, you shall be able to know what are electrocyclic reactions, learn about disrotatory and conrotatory motion in electrocyclic reactions, identify rules governing stereochemistry of product formation in electrocyclic reactions, evaluate various examples of ring closing and opening electrocyclic reactions, analyze and appreciate applications of electrocyclic reactions in nature. Electrocyclic reactions are unimolecular pericyclic reactions characterized by creation of a ring from an open chain conjugated system through sigma bond formation or a ring opening reaction leading to formation of new pi bonds. As you can see in the given reaction which shows ring closing electrocyclic reaction, the movement of pi electrons on application of heat leads to the formation of a new sigma bond and hence a new six-membered ring. The next example is that of ring opening in an electrocyclic reaction. If we start with a four-membered cyclic ring, one of the sigma bonds is breaking to form new pi bonds. The electrocyclic reaction may get effectuated by both heat and light. Generally, the reactions are reversible and their direction is determined by thermodynamic stability of products. Most of the electrocyclic reactions are ring closing and a few are ring opening in conformationally strained rings such as cyclobutene. Along with neutral substituted polyenes, electrocyclic ring closing reactions have also been observed for cationic and anionic polyene species. Following are examples of such reactions. You can see the first equation is showing the formation of a five-membered cyclic ring, whereas the second one is showing the formation of a seven-membered cyclic ring. Now let us look at the stereochemistry of electrocyclic reactions. Electrocyclic reactions are essentially stereospecific. To understand the stereochemistry of electrocyclic reactions, whether it be ring closing or ring opening, it is important to examine the p orbitals on the terminal carbons of the HOMO of the reactant and determine whether like phases of the orbitals are on the same side or on the opposite side of the molecule. You can see in the diagram, the first figure shows where the like phases are on the same side, whereas in the second figure, the like phases of the HOMO of the reactant are on opposite sides. Now this is vital as an electrocyclic reaction occurs only when like phases of orbitals can overlap to form a new bond. Only such a reaction is symmetry allowed. This gives rise to two possible stereochemistries for the ring closing or opening reactions, namely conrotatory and disrotatory mode. When like phases of the p orbitals are on the same side of the molecule, the two orbitals must rotate in opposite directions, one clockwise and the other one counterclockwise for an effective overlap. This rotation in opposite directions is said to be disrotatory. You can very clearly see in the figure where the first orbital has to undergo a counterclockwise rotation, whereas the second orbital undergoes a clockwise rotation. When like phases of the p orbitals are on opposite sides of the molecule, the two orbitals must rotate in the same direction, both clockwise or both counterclockwise for effective orbital overlap. Rotation in the same direction is said to be conrotatory. Two clockwise rotations lead to overlapping of the same phases of the p orbitals in the reactant. What determines if the reaction will proceed with conrotatory mode or disrotatory mode? It is the number of double bonds in the conjugated polyene and the type of reaction that determines whether rotation is conrotatory or disrotatory, as is dictated by the Woodward-Hoffmann rules. According to Woodward-Hoffmann rules, all electrocyclic reactions are allowed, although it does not necessarily mean that the reaction takes place. The rules are as follows. If the number of pi electrons are 4n, the reaction under thermal conditions will show conrotatory motion. 4n plus pi electrons, on the other hand, in presence of light will show disrotatory motion. Likewise, when the number of pi electrons is 4n plus 2 and the reaction is carried out under thermal conditions, the motion will be conrotatory. Whereas for 4n plus 2, when the reaction is carried out in presence of light, the motion of the orbitals will be disrotatory. As an example to understand Woodward-Hoffmann rules, let us consider the correlation diagram for electrocyclic ring closing of butadiene. The 4 pi electrons of the diene form the new sigma bond of the cyclobutene. These pi electrons are valence electrons, which are least tightly held by the nucleus and are present in the highest occupied molecular orbital, that is HOMO of the diene. For butadiene molecule, a two-fold axis of symmetry is maintained throughout a conrotatory electrocyclic closure or opening, while a mirror plane of symmetry is conserved during disrotatory ring closure. The orbital correlation diagrams for electrocyclic reactions of butadiene are shown. As you can see in the diagram depicted, the various orbitals are depicted by dark and light, shaded and unshaded portions. The solid lines connecting reactant and product molecular orbitals, that is MOs, show the correlation for conrotatory ring closure. The MOs being classified according to their properties, that is S or A, with respect to a preserved C2 axis of symmetry. The correlation for ring closure in disrotatory manner is shown by the dashed lines, the MOs being classified S or A with respect to a preserved mirror plane of symmetry. The thermally allowed conrotatory opening of cyclobutenes has been confirmed experimentally. Torque-selectivity is an important feature of electrocyclic reactions. By definition, torque-selectivity is a special kind of stereoselectivity observed in electrocyclic reactions as the preference for inward or outward rotation of substituents in disrotatory or conrotatory reactions. Some of the electrocyclic reactions can also be described by this concept, in which different directions of rotation produce distinct structural isomers. In such cases, the driving force for the selectivity is steric strain. Studies have revealed that the selectivity changes by the presence of either electron donating or electron withdrawing groups. Next, let us talk about reactions and geometry of electrocyclic ring closing and opening. Let us start by considering the 4n plus 2 system. Let us consider thermal ring opening reaction of 3,4-dimethyl cyclobutene, which may exist as cis and trans isomer, to give hexadiene, which may be cis, cis, cis trans or trans trans. The reactions are stereospecific, meaning thereby that for cis 3,4-dimethyl cyclobutene only cis trans product was obtained, while for trans 3,4-dimethyl cyclobutene isomer only the trans-trans diene was obtained. The reactions take place via conrotatory motion about the C3-C4 bond in a 4-member cyclic transition state. Furthermore, it was observed that reverse of ring opening reaction, that is, photochemical cyclization of the cis-trans diene, gave a different cyclobutene than the one from which the diene was formed by the thermal ring opening. As electrocyclic reactions are reversible, whether ring opening or closing will take place is determined by thermodynamics. However, the stereochemistry of product formed is not influenced by the thermodynamic stability rules. This is evident from the examples where the cis-cyclobutene A gave the thermodynamically more strained product B with one of the double bonds in a cis geometry. For the ring closing reactions of substituted hexatriene E, also the formation of cis isomer F proceeds via disrotatory mode, which is also counter thermodynamic. Aromatic compounds can be converted one into the other by electrocyclic reactions. For example, cis-stilbene can be converted to phenanthrenes under UV light in the presence of oxidizing agent such as oxygen or ferric chloride or palladium charcoal, as you can see in the given reaction. The reaction is conrotatory process involving conversion of 1,3,5-hexatriene to a cyclohexadiene, followed by removal of 2 hydrogen atoms by the oxidizing agent. Dear students, next let us talk about a 4n electron system. The light-driven electrocyclic reactions are known with 4n number of electrons. These are reversible reactions as upon heating the product, they give back the starting material. In the octatriene system with 8 electrons, conrotatory closure gives rise to cyclooctatriene. The reaction product undergoes a further electrocyclic reaction, giving the bicyclic diene as the final product, as shown. Dienyl cations as well as anions both undergo electrocyclic ring closure. When cyclooctadiene is deprotonated with butyl lithium, we get cyclic ring closure as shown. For pentadienyl cation, which is a 4-electron system, ring closing reaction takes place via conrotatory motion, giving the stereochemistry as indicated. Interestingly, in the reaction, both C1 and C5 might carry the delocalized positive charge, and still bond formation takes place between the two atoms. This is unlikely for polar reactions and is possible only due to electrocyclic nature of the ring closing. Nazarov cyclization is another important example of such a bond formation between two positively charged carbon atoms. Cyclopentenones can be synthesized from divinyl ketones. This is allowed by Nazarov cyclization. In the following reaction, a cross-conjugated dienone forms a cyclopentenone when treated with a Lewis acid. The relative stereochemistry at C1 and C5 in the product is trans, thus confirming conrotatory mode of cyclization. An important feature of the reaction is role of silyl group present in the side chain to determine torquoselectivity of the reaction. It is geometry of the silyl group that determines anti-clockwise rotation, so that lower lobe on C1 turns upwards, presumably because it is anti to silyl group, which is a large donor substituent. Next, let us talk about the allyl system. Electrocyclic reactions in cationic allyl systems have been known to take place. Opening of cyclopropyl cation to an allylic cation is an example of smallest system capable of undergoing an electrocyclic reaction. When the participating electrons are 2 in number, the reaction is disrotatory. In the reaction, removal of the tosylate, that is OTS, and ring opening occur simultaneously. Therefore, a cyclopropyl cation is not considered an intermediate. Cyclization of allyl cation is an intermediate step in Favorowski arrangement also. Arrangement of cyclopropanones and ketones containing halogens at alpha position, which lead to formation of carboxylic acid derivatives, takes place in Favorowski rearrangement. For cyclic alpha haloketones, the Favorowski rearrangement constitutes a ring contraction step as shown. The first step of the reaction comprises of an electrocyclic ring formation in concert with removal of bromide ion. The reaction is driven in the forward direction because the oxyanion of the enolate stabilizes the cyclopropyl cation in the intermediate. The final step in the reaction is ring opening to give ester product. The reverse of ring opening is cyclopropyl cation, that is, ring opening has also been shown to take place as shown. In the intermediate, allyl cation is formed, which is short-lived as halide anion quickly captures it on the same surface. Next, let us talk about naturally occurring electrocyclic reactions. Electrocyclic reactions occur very often in nature. An important example of electrocyclization step is the biosynthesis of vitamin D3. The biosynthesis further involves a 1,7 hydrogen shift for the formation of the final product. As you can see in the equation written below, 7-dehydrocholesterol undergoes convertatory reaction in presence of light to form pre-vitamin D3, which after a 1,7 hydrogen shift gives us vitamin D. Let us now try to do some examples on electrocyclic reactions. As we already know, pericyclic reactions are reactions in which a cyclic conjugated system is created in the transition state. The Diels-Alder reaction is a common example. Electrocyclic reactions are a subtype of pericyclic reactions, which is unimolecular and in which the termini of a conjugated system become sigma bonded to each other to form a shortened pi system. The reverse of this, that is the cleavage of a sigma bond to generate a longer conjugated system, is sometimes called a retrocyclic reaction. As an example of the latter, cyclobutene is cleaved thermally to yield 1,3-butadiene, relieving the extensive strain in the cyclobutene system and gaining the resonance stabilization of the conjugated diene system. The alkene pi bond of cyclobutene is extended to give the conjugated system of butadiene. The specially interesting thing about this reaction is its stereochemistry, as revealed, for example, in the cleavage of cis and trans 3,4-dimethylcyclobutadiene. The reaction is highly stereospecific, with the trans isomer of the reactant yielding the EE isomer of the diene and the cis isomer of the reactant giving the ZE isomer of the diene. Note that in the IUPAC nomenclature, E or antigen means trans and Z or Zusammen means cis. The observation of stereospecificity means that in both transition states, for the two isomers, a single rotatory pathway is followed, yielding different isomers of the product. In particular, the groups attached to C3 and C4 must rotate in the same, that is either both clockwise or both anti-clockwise direction. The term which is used in this connection is called conrotation. In cis 3,4-dimethylcyclobutene example, the two methyl groups both are shown as rotating clockwise. This yields the cis trans, that is the EZ isomer of the diene. On the other hand, in the trans isomer of 3,4-dimethylcyclobutene, if clockwise rotation is followed, the trans-trans, that is EE isomer of the diene is generated. Note what is not observed, vis-a-vis disrotation, in which the groups attached to C3 and C4 rotate in opposite directions, that is one clockwise and one counterclockwise. In such a case, the cis-cyclobutene isomer would give rise to EE24-hexadiene and the trans-cyclobutene isomer would yield EZ24-hexadiene. That is the opposite results from what are actually observed. So, the reaction as experimentally observed are not disrotatory, nor are they a mixture of disrotatory and conrotatory paths, but they occur exclusively by a stereospecific conrotatory pathway. It will be of interest to examine the reason for this preference. Incidentally, electrocyclic reactions in large or smaller rings always have strong rotatory preferences, but not always for conrotation. That is, some strongly prefer disrotation, as we shall see in the given diagram. Let us now summarize this module. Electrocyclic reactions are unimolecular pericyclic reactions characterized by ring closing or ring opening in concerted fashion. Electrocyclic reactions are reversible in nature. Thermodynamics decides the direction of an electrocyclic reaction, that is ring closing or opening, although the products of the reaction may be counter-thermodynamic, that is, thermodynamically less stable alkenes may be formed. Electrocyclic reactions are stereospecific essentially. In electrocyclic reactions, there are two modes of bond formation, viz. Conrotatory and disrotatory. When like phases of the p orbitals are on the same side of the molecule, effective orbital overlap requires the two orbitals to rotate in opposite directions. This rotation, which is in opposite directions, is referred to as disrotatory. When two phases of the p orbitals are on the opposite sides of the molecule, the two orbitals must rotate in the same direction for effective orbital overlap. Conrotatory refers to the direction of rotation which takes place in the same direction. Woodward-Hoffmann rules predict stereochemistry of product formation in electrocyclic reactions. For 4n plus 2 and the 4n systems, thermally conrotation gives rise to direction of rotation which takes place in the same direction. Woodward-Hoffmann rules predict stereochemistry of product formation in electrocyclic reactions. For 4n plus 2 and 4n systems, thermally conrotation gives rise to the product. For 4n plus 2 and 4n systems, photochemically, disrotation gives rise to product. Torcoselectivity is a special kind of stereoselectivity, which is a measure of disrotatory and conrotatory mode of rotation in electrocyclic reactions.